okay, the nuclei can be imagined like this big nucleus here, formed of proton and neutron, and there is continuous interaction. Okay, this nuclei tends to split apart because of the electrostatic forces, and tends to stay in one piece because of the binding energy. And we said that the binding energy is determined by the mass of the nuclei minus the mass of the individual protons and neutrons. Okay, that's what we said last time. Now we said that we have 3 types of radiation: alpha, beta, and gamma. So if we go on for the alpha, and we discussed about the decay constant, the half-life time, and the activity. These are three ways to account for how fast the change in the nuclei is occurring. Once again, I would like to remind that this is, for example, if you count here 16, let's say 16 radon at nuclei. These 16, they go into, after T1.5, they go into 8, they become 8. The others, they become something else. Okay, this is very important to remember. So they become something else. All right. This is the activity, and these are some of the radioactive material, and we have discussed this last time. So let's go for the alpha. So the alpha decay, we lose 2 protons, 2 neutrons. So basically, this is the helium 2+. This is the helium atom without the electrons. Okay, so you have 2 electrons, 2 protons, and 2 neutrons. And so clearly, if you lose 2 protons, 2 neutrons, this means that the daughter nucleus, Z will become Z-2, and A will become A-4. So this must be conserved at all times. Okay, this is an example where you have a radon 22688. Half-life time decay is 1600 years. Okay, so once it splits, the radon turns into radium. Radon turns into radium. Okay, and emitting of an alpha particle. Now, of course, this alpha particle, because initially the kinetic energy and the momentum is equal to 0 because it's just one nuclei. Then once it's split into 2 different masses, then the alpha will have a huge amount of kinetic energy with respect to the radon. Okay, because the total energy must be equal to 0. Okay, and because of the difference of the mass. All right. So using a momentum and conservation energy, we can determine the velocity of the particles of the alpha and radon particles, or the daughter particles. Okay, this is another example. You have uranium. You've definitely heard of uranium, which is a 23892. It goes into thorium, which is 23490 plus a helium. Okay, that's the radioactive. Now, the beta decay. So we can imagine. Go back to this picture here. The picture. This one, I can imagine. You can imagine this thing is boiling. Okay. And at some given point, there's one chunk which gets out. Okay, this is the alpha particle radiation. The beta is quite different. All right, the beta is trickier. Right. So the beta decay actually we have what you call a mutation. That's the right word that you guys need to remember. A mutation of a neutron into a proton, or a proton to a neutron. Okay. And so this is quite different from this chunk of particle going outside the nuclei. And so now a neutron turns into a proton, which is charged positively. Now, in order to conserve the charge, okay, then it must emit an electron. Okay, a proton, when it mutates to a neutron, it goes to from plus to 0. Then it's going to emit a positron, E plus. Okay, so E plus and E minus, these are matter, these are elementary particles, okay, with the same mass but different charges, opposite charges to be more exact. Okay, so so it emits a positron, and this nu is called a neutrino, and new bar is going in antineutrino. We'll come to that in a few seconds. Okay, so in alpha particle we have a chunk of the nucleus which goes away. In beta, it's absolutely not like that. It's really a neutron. It mutates. You have the issue of mutation of a neutron and a proton. Actually, this is going to be an indication that neutron and proton are not elementary particles. They are formed of other particles, okay, so that they can mutate. Okay, elementary particle like the electron, it doesn't change. Whereas a neutron, as you can see clearly here, it changes. Okay, it goes from a neutron to a proton and vice versa by emitting other elementary particles. So since we have in one case I have neutron less and the other case I have a proton less, then symbolically when I have when the same number of A's, in both cases the total number of proton plus neutron remains the same. So A is the same, but one I lose one proton and one I gain one proton. See, when I go from neutron to proton, I gain one proton. And when I go from proton to neutron, I lose one proton. So this is one, when I gain one proton, so Z goes to Z plus 1. And when I lose one proton, Z will go to Z minus 1. Now, as you see these symbols, the figure below here, okay, it's just for your general information, is that what it turns out that the proton and neutrons are formed of particle which called quarks, okay? And the proton is formed out of two types of quarks, but with three, up, down, up quark, and neutron is up, down, down quark. And so these quarks, they can change, okay? They can change, going, for example, from down quark to an up quark, and now we go from a neutron to a proton emitting an electron and an antineutrino. So that's just for your own basic information. So the question is that could be raised is that, okay, why do we have this antineutrino business? Why? I mean, where does it come from? Okay, if you look at this reaction where we have nuclear reaction, that the carbon 14, there's a nitrogen 14 which is daughter plus an electron which is a beta particle. Now the nice thing about electrons is that I can measure their energy. I can measure their velocity, okay? I can put them into a magnetic field, and depending on where it hits, then this gives me the energy of the electron. So I determined that, okay? And now what I can do is I plot the number of beta particles, the x-axis you see on the figure here, okay? And the kinetic energy. So I can compare experiment to theory, okay? As I told you before, if I remove the antineutrino, the carbon 14, the energy is equal to 0 and the momentum is equal to 0. Consequently, the energy and momentum for the nitrogen and the electron are very different from 0. And thus my calculation is exact and simple and exact, the two. So simple and exact, doesn't require a lot of mathematics. And so my kinetic energy for the electron is determined accurately, okay? Now, with the experiments that we have, we can also determine the energy of the electron very accurately, okay? So now what we do is that we plot the x-axis is the number of beta particles, basically the electrons, and on the x-axis the kinetic energy. And I'm going to compare the experiment to the theory. And what people found is that the kinetic energy that's been calculated, Ke max, okay, there's almost no electron there. Most of the electron is here. Energy is much smaller than Ke max. Consequently, there is another particle which took this energy, and this particle must have a mass which is much smaller than the electron because it takes all this energy from the electron. Okay, and this is the reason why people invented what we call antineutrino, or another particle that at the time where this experiment took place, there was no evidence of its existence at all. Okay, but of course later on it was determined, and the lifetime of it is determined. Is now a well-known elementary particle in physics. Okay, So this is why we need to add these neutrinos and antineutrinos, and this was discovered by this missing energy by Pauli, okay, who had other contributions and won the Nobel Prize in 1938 for physics. Okay, so this is the beta plus emission again. So the question is, okay, now what happened to this beta plus? In nature, guys, antimatter, okay, this is the matter that we know about with the same mass but opposite charges. They live in our universe for a very short time. Okay, so what happened to this positron? Why don't we have positrons around us? Okay, the reason why we have positrons is that it immediately become a photon. Okay, you tell me, oh, I mean, an electron, a positron, is the same as electron, right? And how come it becomes a photon? I can reply by saying that E is equal to mc squared. And so my mass is converted into energy by emitting two photons. You see this gamma, these gamma particles, okay, which go in opposite direction, okay, for here also for the reasons of conservation of momentum. Okay, so usually these positrons or these antimatter particles, they turn into photons. Okay, they are so they turn into photons. There is a movie by Dan Aykroyd, I think, not Aykroyd, on where they start harnessing this antimatter. Okay, and today there are people with their goal is to harness this antimatter and maintain it in the containers, and so it does not undergo this kind of reaction. Okay, so this is emission and annihilation. So please remember, all right, I don't think that we're gonna come back to this during this class, okay, but please remember, E is equal to mc squared. So mass can become energy, but energy can become mass. Okay, so if I have two gamma rays, two photons, okay, with the right amount of energy, and I put them close to a massive particle, then these photons will act like particle, and they could become actually a massive particle. So we can convert from energy to mass. Here, we are converting from mass into energy, into photons. Okay. We come to the third component, which is the gamma rays. The gamma rays are basically just like, these are electromagnetic waves, like the visible light, like the X-rays. I put here where you can see that the energy is very high, okay, with respect to the X-ray and certainly with respect to the visible light, okay. And so basically how to imagine what's happening inside the nucleus. Well, what it turns out that what's happening inside this very tiny part is actually a little bit similar to what's happening for the atom. And that is these protons and neutrons, they have discrete energy levels, okay? And they get excited and disexcited. And when they get disexcited, they emit the photon. So basically, it's exactly the same mechanism as for the electron excitation and disexcitation, but now it's occurring at a very tiny scale. For this reason why you can see that this bottom scale here, you see the lambda in meter is roughly 10 to the minus 15, 10 to the minus 14, and 10 to the minus 12. Because this transition is occurring at the nucleus size and not at the atomic size, where it may be emitting in the angstrom or the nanometer scale. Okay, so in this case, we don't have actually change in the nature of the nucleus. We just have a more stable nucleus. Okay, so for example, one way of the beta decay can take place is that we have this boron at 12.5. It goes into an excited carbon. So with plus one electron. Notice here, I don't have a neutrino or antineutrino, but my neutron, but by my nucleus is excited, and now I go from an excited carbon to a disexcited carbon in the ground state by the emission of a gamma photon. Okay, so this is another way for the beta decay, also for other nuclear reaction. So So basically what this serves is that this serves as an excitation of the nucleus. Yes, Rayyan, this also applies to light, but you have to have, first you have to put these lights in a special way, okay, such that they conserve momentum mainly, okay, and you have to put it in close to a massive particle, so that these light, which are photons, mass equal to 0, okay, they become mass different from 0, okay, so it's not only for positons, but also for photons, okay? And what I'm trying to say here, guys, and I hope this is clear, that this reaction here is, you could go from positron to 2 gamma rays, and you go from 2 gamma rays to a positron. It's not a one-way, it's two-way reaction. Okay, but of course now the gamma rays must be in this direction, opposite and opposite direction, and they have the same energy and the same momentum, such that the conversion can take place. I hope this is clear for you. Okay, so let's talk for one minute about the carbon dating. I think that most of you have heard of carbon dating. Okay, and that is the way that we use the carbon 14 and carbon 12 in order for us to date the last time that the being was actually alive. The process goes as follows. First, you have these cosmic rays, okay? These cosmic rays, which gives us neutrons. These are coming, usually they come from the sun, okay? They come and they interact with the nitrogen 14 in the upper atmosphere, okay? This nitrogen 14, so this neutron combine with the nitrogen to become a carbon plus a hydrogen atom, okay? So basically this is always happening, okay? So you have these flux of cosmic rays, and so always on Earth you have these generation of carbon 14, all right? And so carbon 14 goes into the chain, okay? The carbon chain, the carbon loop, okay, of food, all right? Of breathing in the trees, all right? And so they become, they are actually now, they are an inherent component of our structure. So we contain carbon 14. However, when we die, or when the tree dies, for example, then there's no influx of this carbon 14. So the carbon 14 stops at the moment where these beings stop breathing, stop eating, stop drinking, okay? And so now this carbon 14 has a very specific property. It has a half-lifetime of 5,730 years. Consequently, if now I count, if I determine the ratio of the carbon 14 to the carbon 12, okay, I know that in all living organisms today, okay, in our body, we have carbon 14 divided by carbon 12 to be roughly 1.3, 10 to the minus 12, okay? But now, so if you measure this quantity, okay, and found, let's say it's 10 to the minus 14, this gives us an idea when this living organism died, because at this point he stopped inhaling or bringing carbon 14, and so this, the amount of carbon 14 with respect to carbon 12 will decrease. If I measure this decrease, then I'm going to have an idea based on the half-lifetime. I can have an idea when it actually stopped taking carbon 14 into its living organism. I hope this is clear. Okay. So let's call it natural radioactivity. So what we said is that with the natural radioactivity, we have unstable nuclei are found in nature. They give rise to natural activity. It's very important to remember that this natural activity occurs all the time, as we speak now, everywhere in the world. All the uranium nuclei are undergoing radioactivity, but of course with different lifetimes, okay? So basically you can see here that uranium-238 goes into thorium, the thorium goes into palladium, the palladium goes back into another form of uranium, but each of these has a different lifetime. So just go back on this lifetime slide. So this is, for example, the uranium-238, okay, decompose in roughly 5×10 to the 9 years. It was very, very, very stable. Okay, so that's why actually we found uranium today on Earth. All right. And now we go into thorium. It has, let's say, 10 to the 3 years or 10 years, etc. So these are all these individual radioactive natural radioactivity occurs. Okay, but at different time scales. Okay, so for example, it takes 10 to the 9 years to go to the half lifetime of uranium to thorium, but then takes, let's say, 1 million years to go from thorium into palladium, and then let's say it takes 10 to the 7 years to go from palladium to uranium, etc., etc. Okay, and now the types of radioactive reactions, as we said, we have 3 types which can change the nature of the nucleus. One is the alpha particle, where you lose 2 proton, 2 neutron. So if the x-axis is the neutron and the y-axis is the protons, so if I'm here, I lose 2 neutrons and I lose 2 protons. Okay. Now, if I have a beta, okay, the beta, as I said, I can lose 1 proton, gain 1 neutron, and I can lose 1 neutron and gain 1 proton. Consequently, I could go diagonally into gaining 1 neutron, losing 1 proton, or gaining 1 proton and losing 1 neutron. So this is one schematic of the lifetime of uranium-238 or uranium-234 until it becomes lead, Pb, which is stable, which is much more stable nuclei. So this is how it can start, and you can see here the different lifetimes for each of these reactions. Okay, when we say finish means that this atom is not radioactive, it's not naturally radioactive. That's what it means. So this is about natural radioactivity. Now, so you definitely heard of nuclear power plants, nuclear energy generating electricity, where they put uranium into these pools and then to generate electricity. So please remember that this uranium is undergoing a nuclear reaction, whether we as humans we use them or not. Okay, so they are occurring in nature. What human did, and they found the process, is to use this energy in a confined manner, okay, an efficient manner, such that we produce electricity. So on the other hand, we have what we call nuclear reactions. Nuclear reactions is basically man-made, usually, okay, or this can be also done in the sun because it requires a lot of energy. And this is what we call a fusion. Someone asked me about fusion reaction. This is a fusion reaction of a lithium-6 with deuterium, H2, you see. Okay, they form a nuclei which is very unstable, so immediately it breaks into two alpha particles, okay? And so, but this nuclear reaction, it can require energy or it can give us energy, okay? So the rate at which reactions can occur depend on the particle energy, the particle flux, and the reaction cross-section. So I don't know if you guys know what reaction cross-section is. That if I have 2 nuclei, okay, I cannot say that these 2 nuclei will actually interact. What I can say is that they have a probability of interaction. This probability of interaction is called the reaction cross-section. So it's just a probability, all right? Okay, so let's take this reaction here. I'm gonna have a helium-4 interacting with nitrogen-14, giving me a hydrogen atom, so 1,1, plus some unknown quantity, unknown nucleus. So in order to find this unknown nucleus, I take the sum of of the helium plus nitrogen, that is 18, minus 1, this gives me 17. And now I have 2 plus 7, that should give me 9, minus 1, that's 8. So in this way, I make sure that the number of neutrons and protons are exactly the same on both sides of the reactions, okay? So, and this is my helium 4 becomes nitrogen plus oxygen plus a hydrogen atom. And that's the Rutherford experiment. So, once again, we go back to our friend Mr. Einstein. E is equal to mc squared, okay? So we are going to distinguish, we're going to categorize these reactions into two types, exothermic and endothermic. Exothermic, this means there's a mass loss in the reaction and there's a release of energy. Exo means outside, okay? So we have this, these particles and they emit these energies, okay? Endothermic is that there's a gain of mass, and there's a gain of mass in this nucleus. This means that we have to come up with the mass, so we have to come up with the energy, and that's why Q is negative. This means that you need to supply this energy in order for this reaction to take place. So Q is positive, the reaction will take place independently of us, okay, and it will give us energy. We can use this energy to produce electricity or something else, okay? In this case, there is a mass loss, okay? E is equal to mc squared. I go from heavy to a lighter, and the difference in the mass is energy equal mc squared, and so that we can get it. It's given to us. In the endothermic reaction, it's actually a little bit the opposite, and that is this reaction will never take place unless we put the amount of energy which will give us the amount of mass to form the particle. In this case, the mass of what we're obtaining is greater than the mass of where we start with. And so we need to come in and put more mass such that this one become this one, okay? And so whether it's endothermic or exothermic is going to be defined by the difference in the masses in the reaction. For example, if we take this deuterium-nitrogen reaction, turn into carbon and helium reaction. And so what you see is that the mass of the deuterium, that's the total mass of the deuterium now, not the individual particle, okay? And that's the total mass of the nitrogen. And then this is on the left-hand side. The right-hand side, we have the carbon, so it's 12, we know that. This is how it's defined, 12U. And we have the helium. If I add all these up, I will end up having that the deuterium plus nitrogen is greater than the carbon plus the helium, okay? So what this means is that energy is converted into energy. So basically I start with bigger, I end up with smaller, and so the rest goes into energy. So that's it's an exothermic energy, and Q is positive. Now, if we go into different reaction, that is the helium plus nitrogen gives me the oxygen plus a hydrogen nucleus, then if you see that the total mass on the left-hand side is 18.0056, and the total mass on the left-hand side is 18.006958. Okay, and clearly now the mass that we started with is smaller than the mass that we end up with. Consequently, we need to supply this amount of energy such that this guy will become as big as this guy. Okay, so consequently, Q is negative. Q is negative, it means that we need to supply the energy. The chain itself, the reaction itself, it's not going to do it. Okay, we need to come in and put this amount of energy in order for this reaction to take place. So what is the minimum amount of energy that we need to supply? If we have reactions such as this one, we have a small nuclei, which is the helium, compared to large nuclei with the nitrogen. The minimum kinetic energy that we need to supply is given by 1 plus small m divided by capital M, the absolute value of Q, which is the difference between the left-hand side minus the daughters minus the mothers. Okay, so this is the minimum kinetic energy. So if the energy is less than this amount, the reaction cannot occur. This is very important. Okay. For the previous examples, for example, the one that we have this one here, the helium and the nitrogen, to give you an idea, an order of magnitude of the idea of the amount of energy that you need to supply. So this is 1 plus the mass of the helium divided by the mass of the nitrogen multiplied by Q, which is the difference in the masses between the daughters from minus the mothers, okay, and the absolute value, of course. So this gives me 1.535 mega electron volt. This is huge, okay, mega electron volt. So this means that we need to supply that, okay, such that this reaction can take place. Okay. Now, usually this is because of the huge amount of energy. To give you an idea, the energy in the sun is order of 1 kilo electron volt. That's in the sun. This is the fusion reaction happening in the sun. So 1 kilo electron volt. This is 1,000 times greater. Okay. On Earth, this is done in what we call nuclear reactors, not the nuclear reactors in CERN, for example, where we accelerate these particles so that this can occur. Okay, now I'm almost done with my lecture here. I think that this is what I think that you guys all know, especially you're studying medicine, is that radiation damage matter in general. For example, to give you an example, I work in a fusion reactor, okay? And gold, if you put a plate of gold, okay, it will become lead. Okay, so you start with gold and then you have lead. Okay, and the reason is that these energetic neutrons or energetic alpha particles or energetic beta particles, what they're going to do is they're going to change the actual atom. So if you recall, we start with the uranium and we end up with lead. Okay, so it changed the uranium. So if you have a DNA, for example, which is formed of the usual 4 elements, and if there's radiation, okay, then this radiation will change the atoms, and so it will change your DNA, and consequently it's irreversible. Okay, there's no way you're gonna treat that. Okay, and this is this is the reason why like doctors who are radiologists, they put these lead protection, and there's extra protection for them because these radiation are really harmful. Okay. To human beings. So you have a somatic damage and genetic damage, reproductivity of the cell, the DNA. Now, this is all not required. So I think I would probably stop there and I'll leave you up to, let me see if there's anything. Of course, radioactive material is used in medicine a lot. For example, this is when you put I-131, which is radioactive material, into the human body, and you trace it, and you trace it so you have information about what the functions and what's happening inside your body. This is the CAT scan. Also, I'm going to leave it to you. MRI, radioactive detector. This is a Geiger, what's called Geiger counter. It uses gas to assess the amount of radiation. So I think that this chapter is done more or less. I mean, it's done. And I really would like to see if you guys have questions for the next minutes.